The increasing demand for higher speed, greater payload, and longer range in aircraft highlighted the limitations of both wood and steel as primary structural materials. Steel provided high strength but resulted in excessive structural weight, while wood lacked durability and fatigue resistance. Aluminum emerged as an ideal alternative due to its low density and favorable mechanical properties, making it suitable for lightweight yet strong aircraft structures. Pure aluminum, although lightweight and corrosion resistant, has low strength and was therefore unsuitable for primary aircraft structures. This limitation led to the development of aluminum alloys by adding elements such as copper, magnesium, zinc, and silicon. One of the earliest and most significant developments was duralumin, an aluminum-copper alloy that offered a substantial increase in strength while maintaining low weight. The availability of such alloys marked a major milestone in aircraft structural design. Aluminum alloys possess several properties that make them highly suitable for aircraft applications. They have a high strength-to-weight ratio, good fatigue performance compared to wood, and excellent formability, allowing them to be rolled, extruded, and machined into complex structural shapes. Additionally, aluminum alloys exhibit good thermal and electrical conductivity and can be produced with consistent quality, enabling reliable structural performance. With the introduction of aluminum alloys, aircraft structures transitioned to stressed skin construction. Aluminum alloys were widely used in fuselage skins, wing skins, stringers, frames, spars, and ribs. These alloys enabled the skin itself to carry significant structural loads, working in combination with internal stiffening members. This approach improved load distribution and reduced overall structural weight. Compared to wood, aluminum alloys offered superior durability, dimensional stability, and resistance to environmental effects such as moisture and temperature changes. When compared to steel, aluminum alloys provided similar structural efficiency at a much lower weight. These advantages allowed aircraft to achieve higher performance, longer service life, and improved safety margins. Despite their advantages, aluminum alloys are susceptible to fatigue cracking and corrosion, particularly in harsh operating environments. These issues necessitated the development of protective coatings, corrosion-resistant alloys, and regular inspection procedures. The fatigue behavior of aluminum alloys also led to the introduction of damage-tolerant and fail-safe design philosophies in aircraft structures. The introduction of aluminum alloys revolutionized aircraft structural design by enabling all-metal, semi-monocoque structures capable of supporting pressurized cabins and high-speed flight. Aluminum alloys remained the dominant structural material in aviation for several decades and continue to play a significant role even in modern aircraft that incorporate composite materials. The Douglas DC-3 is widely regarded as the aircraft that established aluminum alloys as the standard material for aircraft structures. Introduced in the mid-1930s, the DC-3 demonstrated that aluminum alloys could provide an optimal balance of low weight, high strength, durability, and manufacturability, making long-range, reliable air transport economically viable. Early all-metal aircraft initially used steel, which provided high strength but resulted in excessive weight. As aircraft speeds, range, and payload requirements increased, there was a critical need for a material that was lighter than steel, yet strong and fatigue-resistant. The development of aluminum alloys, such as duralumin, aluminum-copper alloys, addressed these limitations and enabled more efficient structural designs. The DC-3 primarily used duralumin and other aluminum-copper alloys, which offered high specific strength and good fatigue performance. These alloys could be heat-treated to enhance mechanical properties and were well-suited for sheet metal construction. Corrosion protection was achieved through cladding, aluminum clad, and surface treatments, improving service life. The DC-3 employed a semi-monocoque fuselage, where loads were shared between frames, stringers, and a stressed aluminum skin. The wings were also of stressed skin construction, eliminating the need for external bracing. This configuration significantly reduced aerodynamic drag while improving structural efficiency and damage tolerance. The introduction of aluminum alloys enabled mass production using sheet metal forming, riveting, and standardized components. Riveted joints became the primary load transfer mechanism, allowing consistent quality and repeatability. Compared to wood and fabric aircraft, aluminum structures required less manual craftsmanship and supported large-scale industrial manufacturing. The operational performance of the Douglas DC-3 clearly demonstrated the advantages of aluminum alloy aircraft structures. The aircraft made its first flight on December 17, 1935, and was configured as an all-metal aluminum aircraft with a typical crew of 2 to 3 members. The DC-3 offered excellent range, substantial payload capacity, and high operational reliability, proving that aluminum alloy structures were not only lightweight and strong, but also durable enough for continuous commercial airline operations, as well as demanding military service. The Douglas DC-3 set the template for modern aluminum aircraft structures, influencing both civil and military aircraft for decades. Its success confirmed aluminum alloys as the dominant aerospace structural material until the introduction of advanced composites in the late 20th century.